All right, welcome. Today we're going to be talking about properties and changes, which are pretty fundamental things to discuss when talking about matter. You might have noticed something interesting about humans, which is that humans love to classify. We classify all sorts of things and in all sorts of ways. We have classification systems for animals, various classifications. We classify numbers, we classify instruments, and scientists in particular are like children with a big box of miscellaneous toys, and we're trying to always sort them into different areas to make them make sense to us. And chemists are no different. And we love to then classify the matter that we study. And there's lots of different ways to classify matter. We can try to classify them in terms of composition. What are they like at the particle level? Are they all the exact same kind of particle, so a pure substance, or are they a mix? And if they're mixed, are they mixed thoroughly with even ratios or not? And that leads us to some of those classification systems. But another way that we can classify matter is by its properties. We classify matter by properties. And specifically, there's two physical and chemical properties, two types that we often then use to classify substances or elements or objects. And those then lead us to different ways to talk about it. For example, when we talk about the categories of metals, nonmetals, and metalloids, we're using physical properties to separate them into groups. Do they conduct electricity? Are they shiny or dull, brittle or malleable? So those are physical properties, and that leads us to one particular classification system or way to talk about them. We can also classify matter by their chemical properties, and that's really a big part of the history of the periodic table. The periodic table was developed by grouping elements based on their chemical properties and their reactivity. So we want to be able to understand the difference then between these two words here. However, in order to get at that, what we really need to talk about is the difference between physical and chemical changes. Because the understanding the difference between the properties really hinges on understanding the difference then between a physical and a chemical change. It's actually even kind of part of the definition then of the physical versus the chemical properties. So let's start then with a physical change. A physical change is defined as when some type of change occurs to the matter where the chemical identity of the substance remains the same. So, for example, I have a piece of modeling clay here, and I can change it. I can, tear it in half, or I can, have a smaller bit now, and I can change its shape. Now, there are some properties about the clay that changed. It now has less mass. And a smaller volume. It takes up a little bit more space, a little less space, and then its shape has overall changed. But at the particle level, its chemical identity is the same. It's the same substance. Now that one's a little bit straightforward, but let's talk about one that sometimes trips up the layperson a little bit more. So let's talk about the process of boiling or evaporating. So I have a pot of water, and I put it on a hot plate or on my stove, and I can turn that water from the liquid phase into the gas phase. The properties here change quite a bit more. And not only do we still have some of those same, change in volume, we actually have a change in density as well. So the physical properties are a little bit more drastic, going from I can really see the liquid water, and I can't see the gas, the evaporated or boiled off water. But the chemical identity of the substance remains the same. So probably most of you are pretty familiar with water's chemical formula or its little structure. So here's a model of a little water molecule. So we have our little oxygen and two hydrogens. So that's the chemical identity of water. And water in the liquid phase is just like this. We got a bunch of them just together, behaving as a liquid, really close, but able to move around and flow at each other. But when a pure substance reaches its boiling point, these can then separate from each other. Ta-da! There, I have modeled the process of boiling. Water together, water apart. But the chemical identity of the substance has stayed the same. It is still an H2O molecule. However, if I take that same water and I run electricity through it, as I have here in this diagram, we have our little battery and we have an electrical current going through the water. It's a little hard to see in the picture. If you look really closely, there are bubbles being generated. And this can seem then fairly similar. We have pure liquid. We have an energy source. For boiling, it was our hot plate. For this process, which is known as electrolysis, it's electricity. And both of them end up with something in the gas phase. The difference, though, is that chemical identity. So we started with this, our water molecule, and through the process of passing electricity through it, we actually end up with completely new substances, oxygen gas and hydrogen gas. So you can see that in order to take this model and turn it into these models, I had to completely change the substance. So the chemical identity has been altered. Bonds had to be broken, new bonds had to be formed. And so this is not a physical change, even though it could on the outside look kind of similar. This is a chemical change. So a chemical change is a change where the chemical identity of the substance is altered in some way. So you're always going to end up with some new substance or substances. Like in this case, we went from water to oxygen and hydrogen gas, which has very unique properties. So here are just some kind of standard examples of physical and chemical changes that you might be familiar with. And so all of these physical changes here, dissolving, any phase change at all, shredding, the key is that at the molecular level, at the level of the particle, if you could zoom in and look at it, the chemical identity has remained intact. It's still the same substance, though it can be in a very, very different, perhaps even unrecognizable form. These chemical changes, what makes them chemical changes is that the substance has been chemically altered. It is now something new. Maybe it combined chemically to make a new compound or broke down, decomposed to make its elements, but at the particle level, bonds have broken and new bonds have formed, and so it's a chemical change. So now we're ready to go back then to properties, because once we understand a chemical change, we can then understand the definitions for physical and chemical properties. A physical property is a property or characteristic or trait of a substance that you can observe or measure without a chemical change having to occur. So it doesn't have to undergo this for you to measure or observe it. So for example, the boiling point of water is a characteristic of it that we can measure without having to undergo a chemical change, because the process of boiling is a physical change. A chemical property, sorry, my face is a little on that definition, is very similar in definition, except we can only observe or measure it during that chemical change, also known as a chemical reaction. So the chemical reaction has to take place in order to observe or measure it. So here's an example, flammability. If I tell you that something is flammable, we can only test or measure that by causing it to engage in that particular chemical change. So by saying it's flammable, I'm talking about its ability to engage in a chemical change and become a new substance. So here are some common examples of physical and chemical changes. Sorry, this word up, properties. I was right. Properties. So physical properties include things like density, boiling point, magnetism. Again, we could observe those without having to chemically alter the substance. Chemical changes, flammability, the heat of combustion, at what temperature will it burst into flames? Because that bursting into flames, because combustion is a chemical change, that's an example. And then pH. On all of those are chemical properties because they relate to it undergoing a chemical reaction. So as chemists, we care about properties not only because it helps us understand the world a little bit better, but it also helps us to interact more safely with the chemicals or the matter that we might be working with. We store it differently based on, if you have something like that's really flammable, we don't want it to be next to something that's likely to spark. So we use things like their reactivity and various properties to help us work with it and store it safely. So there we have it. Keep a really good idea on your learning objectives page to make sure that you feel comfortable with the learning outcomes that you're expected to know based on this content. And hopefully now you have an even better understanding about how scientists use properties and changes to classify and describe matter.